Okay, so I've gotten some things graded, got exams graded. We'll talk, I don't usually talk lots and lots about exams in class because, well, everybody did different things on them and so forth, so it's better to, I think, talk one-on-one about any particular things on the exam for the most part, unless there's something that sort of everybody had trouble with. Along those lines, then, yeah, you know, everybody, almost everybody, I should say. Well, I'll go with everybody. Everybody had some problems with, well, let me find the exam. Oh yeah, number 11. That was hard. Okay, it was meant to be hard, and I don't know exactly the answer to it. Okay, I mean, it's hard. Now, why is it hard? Well, because it's got that darn sine, you know, there's a sine function and the x out there, and the fact that when you take the derivative, you get an x on the outside of the sine. Generally speaking, when that happens, it just plain gets hard. So, so in 11, you had what? F of x is sine of ax squared.
Mr. Dillon?
Oh, did I not switch back?
No, sir.
No. Yes.
Are you presenting to him?
Yeah, I think I am. Are you seeing it?
No, sir.
Oh, you're not. Okay.
Did you present yourself?
I think I did. Let's look. Where is it? There we go. Oh, it turned off. I went up there for yelling out. Screen. So I wonder if okay, so we're there. The sine of ax squared and then plus x over 2. And so let's go back to the board. Or maybe I hit a key or something like that when I switched between them. Or maybe I'm just getting senile. I don't know. That could be true too. Plus x over 2. And the big problem is that, yeah, we just want to take the derivative, set it equal to 0. So I do that, and I'll get my cosine of ax squared, but then times the derivative of what's inside, which is 2ax. So I'll put that out in front. And then plus 1/2, and I set that equal to 0. And even if I know what a is, it's hard. Okay, I mean, it's hard in the sense that you have to solve it numerically. Okay, so then what makes it doubly hard is I have to solve it numerically, and I don't know what a is. Right, it's just a parameter. And so really about the best you can do is try some different values of A to come up with what that X would be and where it would be. Now graphically, we can kind of see what's going on. So I don't remember everything I have graphed here, but there's my function, and that's in red. I don't think this is in projector mode, so we'll make it a little bigger. I had to set A to something or other, and I think I probably started with it at 1. And I think that blue line, no. What is that blue line? Oh, okay, so that's a particular value with A to the 0.54 and so forth. So let me put this in. Okay, so that's also a blue line. So turn off the derivative for a moment. That's the same derivative. So as you're looking at this, we're going from 0 to that blue line. And so graphically, I can see, and so I set this up so I could just kind of look. And all that happens, and a couple of you mentioned this, I think, that when I change A, if A gets bigger than 1, it sort of squeezes everything in. If A gets smaller than 1, it expands everything out. And, whoa, way out. And, but the picture pretty much always looks the same. So graphically, and since I have to do this numerically, I can see that the minimum is down here at 0, 0, 0. I can just see that because that was the closed interval from 0 to then this blue line of square root of pi over A. And so that's always the minimum. So that part's a piece of cake. I can get that. But this maximum here, it's at 1.327 and has a height of 1.6455. Where the heck did that come from? And if you play around with it a little bit, there's really no good answer. I mean, you're kind of hoping that, maybe the answer's like, X equal, I don't know, like pi over A or something like that. Or the square root or the cube root or something. No, it doesn't appear to be anything like that. And so what you can do is you can try different values of A and get some answers. And then you can plot them. And this is where X1 here is actually my value of A. And Y1 then is the X value that goes with it. I didn't relabel anything. And if you zoom out, you can see those blue dots. Let me get rid of that thing. How many should I have? 5? 1, 2, oh yeah, out at 10, so I have to come in there. And so I looked at that and I thought, well, what the heck is that? Well, it looks a lot like 1 over x. Right, so I just thought, well, it's something like 1 over x squared, 1 over x cubed, something like that. And so I just took those data and I actually had this thing fit a power function, and it fits pretty well. It came up with an r squared of 0.9999, and that's about as well as I've ever seen. And so it looks like the way it behaves is a lot like this power function where C is 1.32957. Now, that's not a surprise, that 1.32, because when A was 1, where that would be the x1, so this is really CA to the P. When A was 1, you got the 1.329757. And so I thought, well, okay, I'll just try that and sort of see how it does. And I played with it a little bit. And it doesn't do too badly. That was this, I guess this is where is it? Okay. So there is the solution I'm guessing for any given A. And so I'm going to get rid of that and get rid of the dots. And I'll probably get rid of that too. And then put the function back in. And notice right there, whoops, other way. You know, my blue line does a really good job of going through the maximum. But that's not too surprising. And so what I did then was, you know, I just kind of looked at what happens as you do this. And if you look at that, when I've got A at 4.75, you know, if you look carefully there, I'm not quite hitting the maximum, right? It's off a little bit. But it's not real bad, right? You know, so I found a way to numerically sort of guess about where the answer is, but I don't have the right answer. Okay, so this was really hard. And, you know, the best solution I saw was someone who just tried, I don't know, maybe 5 or 6 different values of A and kind of got a good idea of what it was. And so, you know, as I say, this one was hard. But that's okay. I mean, you know, so now how did I grade it, so to speak? There were 96 points possible, because I just did 4 points for every answer. 96 points possible. So I got your raw score, and that's what you see if you know, click on your stuff and look at what I attached. I attached a most likely an illegible copy of your exam, and but it had the comments. Those should have been readable in the score, and so that was out of 96. That was a raw score, and what I did was I added 6 points to everybody's score and called it out of 100. Now, why 6? Well, 4 to make up for the 96. So everybody just got 4 free points that way. And then I didn't expect anybody to get a 4 on this particular problem. So I gave you 2 points for that. You know, so if you got 2 points on number 11, you nailed it from the points perspective. And so that's then, when you look at your reported score, it's out of 100, and it's 6 points. It should be 6 points higher than whatever your raw score set on your exam. Okay, and like I say, I don't usually go into much else. I just let you, you definitely should feel free to come talk to me, if you have any questions on any problems. If, go through the comments and add up your points. What I do is I give points on a page, and then I sum them up and put it down in the corner. So you can make sure every page appears to have been added correctly and that the total sum is correct. So you can take a look at that. So if I ended up reporting too few points, I'm sure you'll let me know. if I reported too many points, it does happen every once in a while, I actually would appreciate you telling me, but I won't take them away. Once on like an 80-point exam or something, I actually had a student come up and point out that, and I think it was a he, but I'll say that he or she, I accidentally gave them 10 extra points when I added them up. And I didn't take them away, you know, but it's good to know. You know, I like to know that sort of thing. So yeah, you know, let me know if I added too many, and I'm sure you will let me know if I added them up to be too few. So, okay. Another item of note. So I haven't, pretty much it comes down to these days, I either have time to create things or I have time to grade things. So the last few days I've been devoting to grading things. And so you also got projects back. What you should have seen, or if you, well, what you have seen or will see. The first project, high scores. I mean, you know, it was hard not to have high scores because pretty much it told you exactly what to do and where to do it and so forth, and you followed directions, and so that was really good. Second project, on the whole, either pretty high scores or pretty low scores. And the big problem on the low scores was it asked you to show the algebraic justification of the limit, which is using the definition and going through all that stuff just like I did. And it wasn't there. Well, that was the main emphasis of the whole thing. And so that garnered really low points. What I would like to do is I'll go with anybody who had below a 36 out of 40. Because, you know, in the end, I mean, it's always good to go through and try to improve your stuff and so forth. But if you had a 36 out of 40, I mean, that is 90%, and, you know, that counts toward an A, and, you know, I don't see a great need to entice you to go back and redo it and so forth. But if you got below that, below a 36 out of 40 on the second project, you are more than welcome to work on a second draft and turn that in, hopefully for a better score. Now, exactly what that score would be, I don't know. You know, so say you did it perfectly and knocked it out of the park. Is that going to be 40 out of 40? I doubt it. But on the other hand, if you do it right, I mean, I'm a big believer in I don't care when you do it or when you learn it, as long as you learn it. Okay, so you know, to me, that's the most important part, is learning it. And so giving you this opportunity and incentive by giving you more points, hopefully that will help you learn what it was we were aiming for on that one. Now, when do you need to get that done? Again, I don't know. As soon as possible. I would prefer it not to be the day before the semester ends, because I'll have plenty to do. I've got plenty to do right now. And, you know, but you can talk to me about it, ask me questions. Certainly you can talk to others in the class. You know, but the idea is try to figure out what it is we were looking for on that. And you are more than welcome to work on it. Let me know if you're working on it. That would be good. And then, given you rework it and turn it in, tell me. Okay, I usually do the needs grading by categories, by like, oh, it's this discussion board, or it's this thing or that thing. And so I won't be looking for it. So it may, so again, it may get there, but if I'm not looking for it, I may not notice it for a while. Probably, again, at some point I would notice it, but could take a while. So let me know, if you turn that back in. I think that is it. Let's see. Yeah. And then I guess one other problem that I did consider hard, but I felt it was doable. I mean, sort of really hard in that you hadn't been assigned a bunch of homework for it yet, and that was the I think finding the closest point to the line. You hadn't really been assigned homework like that yet. That's out of this last section. Things that are phrased like that. So that one I felt was hard, but actually lots and lots of people did quite well on that one. So I was correct, it was doable, but it went a little beyond the material that we had. And all my exams will always do that. They'll have a couple problems that somehow go a little beyond the stuff we've done. Okay. Questions over any of the material? Anything else? Nope. Okay. All righty. Well, yeah, let's look at some of these problems from 3.7. So all 3.7 is really doing is saying, a good reason to know how to take the derivative, set it equal to 0 and all that, is we like to optimize lots of different things. And we like to find minimums and maximums. And so, what I thought I'd do is just kind of look at the problems, look at some of the exercises, and get rid of this. So from 3.7, if we look at number 2, what they'd like us to do is create a box, and they want a box of maximum volume from a square piece of material, and by cutting the corners and turning up the sides and so forth. Now, this is actually one of those problems that I think is pretty good. I mean, this is a nice problem because manufacturers actually do need to worry about this sort of thing. Now, it's usually a bit more complicated than what it has here. Typically, we throw in constraints on materials or something like this. So it could be that instead of square, it would have to be rectangular, but maybe a particular ratio on that rectangle, something like that. But here, yeah, we've got a square box, and we're going to cut the corners out of it to get our volume. And so our picture and I guess the box is 24, or no, the cardboard is 24 total. So from here over to there is 24 inches maybe. 24 something, 24 inches. And then, so is the height because it's square. And, you know, usually with these, it's the big issue is actually just modeling the problem. I mean, once I get the problem, once I have the function that I'm trying to either minimize or maximize, oh, well now it's just back to taking the derivative, set it equal to 0, you know, maybe get on Desmos or something like that to check out the graph. You know, once I've got the model, it's back to just calculation. And then once I get an answer, though, I do need to interpret it relative to the scenario. And so here, to model this, you know, the suggestion is, well, we know this length, but I don't know that length. And so maybe the thing to do is to get the volume in terms of that length, because in the end, that's what I need to determine, is how big to make that cut. And so they point out, they give us a nice hint that this distance is 24 minus 2x. And so if I want the volume, so I want that volume V, then, well, I just need the base area. So that would be 24 minus 2x squared. And then times the height of the box, right? So x times that. Now, I don't like the way that looks. I mean, I'll put the x in front of all that, but that's our volume. So x times 24 minus 2x squared. But see, now I just got this function. I want to make it as big as possible. And so, well, I know how to do that. V prime is equal to, now here's a good question. You know, should I just multiply this out, multiply through by the x, or should I use a product rule and a chain rule here? I don't know. You know, I mean, I could go either way. These are nice enough. I think I'll try the product rule idea. And so I'll take the derivative of x, which is 1, and then multiply by the 24 minus 2x squared, and then plus the x times the derivative of this thing. But that is 2 times 24 minus 2x to the 1. So I took care of the outside part. And then I need to remember to multiply by the minus 2, the derivative of the inside. And so I get that. Yeah, I don't know. You know, it looks like I maybe still have to square that out. But maybe I can get away with not doing quite as much work. I don't know what's more work. But I've got that term there, and I've got it again there. I've got one of them there and two of them there squared. So I could pull that out. 24 minus 2x. Now the reason this might be nicer is it's going to already be factored. So it might be much easier to set equal to 0. So I pull out the 24 minus 2x, and what I have left here is my 24 minus 2x there. And here I just have that minus 4 from those two and the x, so minus 4x. So I think, yeah, that was the better way to go, because, you know, I've got this factor, and then I'll have this factor as well. And so this is 24 minus 2x times 24 minus 6x. And I want to set that equal to 0 to find my critical numbers. And so 24 minus 2x equals 0. Well, that implies x equals 12. And 24 minus 6x equals 0 implies x equals 4. Now, I'm pretty sure the critical number I want is x equals 4. Okay, and now how am I getting that? Well, I got to be a little careful, because this is a cubic, right? If I square this part out, I'll get x squared, and then times x, I get a cubic. So I've got to be a little careful. But actually, just as I look at this function, I can see it's 0 when x equals 0, and I can see it's 0 when x equals 12. Okay, so the volume is 0 here. So I'm kind of guessing that my function, if I look at it, there's 12. I'm guessing the function does something like that. So this is v of x. And the reason I'm guessing that is that I can't believe starting to cut in and turn those boxes up, I would get a negative volume, right? That doesn't make sense to me. It's not physical, right? It doesn't, how would I get that negative volume? And this is the, so I had a critical number here. So again, my guess is, since I know it's a cubic, probably does that. Okay, because I only got 2 critical numbers. It's a cubic. So the most I could possibly get, I suppose, let's see, could I get 3? Because I'm just wondering about the inflection point there. I don't think so. I think I can only get 2 critical numbers at most. So, and I know what a cubic looks like. So if I get these 2 critical numbers, one's going to be a relative min and one's going to be a relative max. And so again, since I know this is at 0, just because of the function itself, I'm guessing without even using something like decimals, it must be doing something like this. Now, and of course, we can check various things. So we got the first derivative here is this. And then I could come back over here and take the second derivative. This would be that, analytical thing. Again, I can go on Desmos and look at the graph of the thing. But if I take b double prime and start with this product, I'll use the product rule. Derivative of the first part, -2 times 24 minus 6x. And then plus -6 times my 24 minus 2x. Okay, so -2, I get minus 48 plus 12x. And then minus, what's 48 times 3? 146? 140, let's see, what did I say? 48 times 3? 144. So 144 plus 12x So this is 24x minus 192. So I have that for my second derivative. And I can evaluate then x equals 4 and x equals 12. Now, again, for completeness, I guess I ought to check 12. But back there at the function value, I know I get 0. So I don't, I don't think I really need to check it. But again, it's one of those things, probably better safe than sorry. So b double prime of 4, I get 24 times 4 minus 192, and that's 96 minus 192, and all I really need to know is it's negative. I don't really care what the value is. I just need to know it's negative. And so this is a relative max at x equals 4. And then, like I say, yeah, we'll go ahead and check the 12. Again, with technology and looking at the picture and all that sort of thing, I don't know that really needs to be done. But if you were telling somebody else about it, you should probably mention something like the value is 0 there, or things like that. So 24 times 12 minus 192. Well, so I've got 96 was times 4, so 3 of those, and so that's what, 288, I think, minus 192, and again, I really don't care what it is, I just know it's positive, and so this is a relative min at x equals 12. And so it's definitely starting to look like that picture to me. Okay, now the question said, let's see, an open box by cutting and turning up the sides. Complete. Now I'm actually looking at the other directions. Analytically complete 6 rows of a table such as the one below. That looks boring. Okay. But I could do that. I could go to Desmos and complete that table very nicely with some formulas. And then write the volume as a function of x. Now, so what are they doing in the parts A and B when they ask us to write a table and so forth? That is worth talking about because often when students are faced with these more applied problems that are modeling problems, often students will say, well, I'm just not sure what to do. And when I talk to the students and ask them questions, what I tend to find is the problem is they're trying to just write down the answer as in the model. They're trying to just write down the model without really going through and thinking about things. And unless you've done these things a lot, usually you can't. And so what they're pointing out in part A when they say, okay, go through and do, here's the height. Okay, it's 1, it's 2, it's 3, and so forth. And length and width. Okay, length, and width. And they say, well, see, it's going to be 24 minus 2 times 1, and then 24 minus 2 times 2, and then it's 24 minus 2 times 3. What they're getting us to do is just say, and it's much like with that problem from the exam, try, if you're stuck, try out a number. Do I just know how to find the volume? If somebody gave me the answer, could I tell you what the volume was? Right? And that's that idea, just, hey, try out some numbers. Can you tell me what the volume is? And so they're getting us to do that. And then what was the third column? The actual volume. And so we do that, and we have our 1 times the 24 minus 2 times 1, and the 2 times 24 minus 2 times 2, and 3 times 24 minus 2 times 3. And the idea is, if you try this for some different numbers, you start to see what's changing, and I'll call that X, or C for the cut, or C for a corner, or an I for I don't know what's going on, but I'll do it anyway, or something like that. So we see that, and that's where we see that, in general, that's what it looks like. Oh, I didn't square that, did I? That's what it looks like for the volume. And so that's why they're having you do that table. They don't, I find the textbooks don't really talk about that when you are modeling, a lot of times, even though you realize you're trying to set it up for indeterminate sorts of things, then with parameters or with these variables or whatever, it's often you need to start by just assuming you know everything. And you can think of it sometimes as checking an answer. Like if I just ask everybody to guess, right? What would you, I'm going to guess 3, I'm going to guess pi. I don't know. I'm going to guess this. Well, how would you check the answer? Well, you would do this sort of thing. And if you think of the modeling process that way, how would I check an answer if I thought I had it? That can help you come up with the model. And I don't say that lightly. I mean, when you get into the modeling, even among mathematicians, that's where I find that, I've never really thought of myself as any kind of fantastic mathematician or anything like that. But over the years, the one thing I've realized is that what I appear to be pretty good at compared to the average mathematician out there is the modeling aspect. I've even known very good mathematicians that when faced with sort of this idea of modeling, relating the mathematics to some real world scenario and trying to get the mathematics to describe it in some way, they're not that great at it. I mean, they're probably better than your basic freshman in college, right? They're way better usually than your basic freshman in college, but it's not necessarily something that just works for them pretty well. And then even me, who it appears I'm pretty good at it, I find there are definitely some areas of application and some types of models that I am just way quicker at kind of seeing how it might all work out than other types of models. And so You know, that's, getting back to this, that's what they're doing, is just trying to give you some heads up as to things you could try in trying to come up with a model, is think of it as, you know, if somebody gave you the answer, said, oh, x equals 5, well, how would you check? You know, think about how you would check that answer. What would you do? And often, that can help you or lead you to the model. Okay, so that's what they're doing in there. Then they say B, you know, write V as a function of X, so there's B. Right, and then they say, go solve it, find the critical numbers, find the maximum value. So we found the critical number to be 4, and so our maximum volume is 4 times 24 minus 2 times 4 squared. Whatever that is, 16 squared is 256, I think. So I believe that's 1024 cubic inches, I think. And again, you know, how do you check? You get on Desmos or something like that. Just plug it in and see. Okay, questions on that? Okay. So, actually, we're just about out of time with talking about the test a little bit. Let me just take the last 2 minutes. I did think of one other thing on the exam that a number of people had a problem with, and that was with the limit. I gave you just some tabular information, and when you looked at the limit as, you know, whatever it was, x goes to 3 or something, of was f over g or g over f or f, whatever, you know. So, you know, something like this, it looked like that. And a number of you looked at that and you wrote down indeterminate. I cannot argue with that word, but I probably wrote something like, what does this mean? Now, what I'm not asking, what does indeterminate mean? Look at your directions. Your directions ask, does the limit exist? And if so, tell me what it is. Does the limit not exist? Or is there not enough information? Okay, so if you just write that that's indeterminate, well, I'd agree with you, but what does that mean in terms of what you were asked to do? Does it mean it doesn't exist? Does it mean the limit is 0? Does it mean the limit is 1? Does it mean the limit's infinity? Or does it mean there's not enough information? And of course, in that case, there's not enough information because that's our whole derivative idea, right? Is that we've got the thing on top goes to 0 and the thing on the bottom goes to 0 to get our derivative. And yet, we have plenty of derivatives out there, so it must be that limit can exist, but it may not exist. So, so that was just one thing that a lot of people did point out, that that is an indeterminate expression, but that's not a complete answer to that question because it doesn't, you needed to state that there wasn't enough information. Okay. All righty. And I will see you on Thursday. And, if you need anything, just be sure to send me an email.
So when the people send my blackboard, it should be fixed either tonight or tomorrow.
Ah, okay.
And then
Cool.
on my test,